I'll be talking about communication amid uncertainty. I'll tell you what we will be talking about shortly. The talk is based on a series of works which are all joint work with Brendan Juba, who is a student of mine at MIT and is now a postdoc at Harvard, and also with Oded Goldreich, and works with Sanjeev Khanna and Adam Kalai. The scope, so let me just sort of roughly, the talk will start off with some motivation, some ramblings. And by the way, I mean, for the students among you, I mean, this must be a real treat because I've been enjoying the morning sessions, and it's really great to hear about sort of different perspectives on what information is and can do for you. I'll also start with my own sort of a perspective on information and computation in particular, and that will lead us to some problem on a sort of a classical question, a new twist on it, the compression problem. This will be a concrete part of the talk, and the third part is sort of, I view it as optional for today. If I get to it, if I have time, I'll talk about it. If not, this is just a warning to say there's much more out there in the papers, but I'm not going to talk about it. So Sergio is not here, thankfully. So
don't worry, record it.
Hi, Sergio. So I should say, how many people know the origin of the phrase of the pair Alice and Bob? It didn't just, sorry?
A and B, though, right?
No, yes, but it started off on there was a moment where it started, just like information theory started at a particular moment with the publication of a certain paper.
It's like Adam and Eve.
Alice and Bob was the terminology used by RSA in their paper inventing the RSA computer system. This is one of their main contributions, they claim, to social discourse. So here's a channel that I want you to consider. So Alice sends a sequence of bits 01, 001, 011, and there's Bob who receives this sequence. And if we manage to work with this channel, then there's this perfect communication, right? We have nirvana. There's no errors. We've got perfect communication. Aren't we done? And I want to suggest that if you're trying to send instructions, maybe these things don't work. So let's try. Alice says freeze to Bob, and Bob immediately rushes into the refrigerator, which is not the response that Alice wanted. So over here, Alice was trying to send a certain instruction. There was a certain interpretation that this is what he would take it to mean and commit to some actions based on this. And Bob unfortunately misunderstood. So it was his misfortune. And this kind of a thing, phenomenon is recurrent. And this is the kind of phenomenon that I want to talk about today. I want to say that this is somehow a new sort of uncertainty. It is not uncertainty introduced by the channel, it's something else. And we want to apply sort of tools of information theory, computer science, to talk about these things. What did our sort of founding father have to say on semantics? You heard this several times in Sergio's talk. He did say, look, the semantic aspects of communication are irrelevant. Okay? And what I'd like to claim is today the situation is different. It was very much true at the time, and we wouldn't be, in fact, making this claim today if we hadn't made that claim then. But semantics are becoming important. Why? One reason is simple. This channel program was widely successful. We had channels which were introducing bit flip errors, and we are still trying to cope with them. We didn't know what to do with it. Then we would be worried about it. But we do know how to handle it. So it's no longer the problem, which is the hardest problem facing us. And so we can start asking the question, can we do what, can we now understand the bits well? And the second reason why the semantics are becoming important is a new interaction between computation and communication. And this is the aspect that I want to talk about in the next couple of slides. So this talk will have a few digressions at the beginning, digressions among digressions among digressions. But we'll hopefully come back to the real story. But let's start with the first digression on communication versus computation. So communication, I think of like phones and so on, computation, think of your laptop and so on. What are the theories behind these objects? What's the technologies behind? One of the remarkable things about stories about these two objects is none of these can exist without the other. Okay? So let me elaborate on what I mean by this. Shannon's architecture of a communication system, what does it have? Two crucial ingredients that he included were the encoder and the decoder. What are encoders and decoders? These are algorithms, these are programs, these are computers. So a reliable communication mechanism cannot exist if you cannot do some computation tasks. Now on the flip side, Turing had this, by the way, sort of up there on the pedestal with Shannon is Turing holding a very analogous state, and they also had sort of some amount of overlap between the two. They were probably spending time at the IIS very close to each other. Turing came up with this theory of computing, and what was the central ingredient in his architecture? There was this infinitely long memory, which is storage, reliable storage that he assumed, and an efficient communication between a finite state control and this the thing that we call the CPU and the memory. And this is communication. This is the bus that runs between the CPU and the memory. And Turing assumed reliable communication, reliable storage of information in order to build his computer. So you have the chicken and egg problem here, right? If you have reliable computers, then you can build reliable communication. If you have reliable communication, you can build reliable computers. And very fortunately for us, we somehow managed to sort of bootstrap our way out of the loop. We managed to build sufficiently reliable, simple computers. We managed to build sufficiently reliable wires. And then bootstrapping out of this thing, we managed to build a system which is extremely, extremely reliable today. Computers are exceptionally reliable, and once you tell them what you want them to do, and communication is extremely, extremely prolific and successful. The technologies, on the other hand, how did they develop? How did the products and the commerce, I mean, if you think of the companies that were involved, and so on, they never really spoke to each other for the longest of times. I mean, how often did Qualcomm or the analogous things ever have to talk to Intel? The early products, computing devices as well as communication devices, had very clean abstractions of the other technology. They said, this is how the other thing is going to work, and we'll never try to put them together. Over time, the situation has changed slowly, and today it has changed completely. Every communication device gives you the ability to program it somewhat. Every computer that you're thinking of has many, many, many communication ports, and they're doing a rich collection of interactions with other computers and other computing devices. So these products are all deeply integrated, and this, I claim, is sort of leading us to this wall. So Turing in 36 and Shannon in 48 came up with these beautiful theories of communication and computing, and they have been kept separated forever. There was a nice brick wall separating them, and this was stayed that way. But semantics is sort of exploring the interaction between the two. When you put the two things together, the wall has to come down. So what are some consequences of the wall? Why is this wall such a big problem? There are two underlying axioms in the two theories which are actually deeply contradictory. The theory of computing has as its core the concept of a universal computer. How many people have heard of the universal computer, by the way? Okay, so fair number of you. This is this thing which says that I can design a computer today, sell it to you, and I have no idea, you may have no idea what software you might be running on it, what algorithms you might want to run on this, but you can program whatever you want onto it. You can change the programming language of the machine if you want. You can change the operating system. Anything, whatever you want to do in this machine can be changed. And if you want this machine, you bought an Apple, you want it to look like a PC, you can make it look like one. Just run a layer of simulator on top, and now, except for a little bit of inefficiency, the looks and feels of it will be identical, and vice versa. You can program your machine to look whatever it feels like. How about the communication principle? You have to take the encoder and decoder, and you have to design them together. There is no notion which says, I will buy a machine on this side and it'll put some encoder on it and hope it will work with some other machine that you buy and you put in your own decoder on it. We have to design the encoder and decoder simultaneously together. And so when you start putting communicating machines together with computing machines, you have to say, which one of these two options do I choose? Do I let you program it or do I not? And you see this divide being, tackled by many, many different machines that you buy. Some of them don't let you touch the software at all, and others let you play around with it, but then you have the issues associated with this. So this is a contradiction, and I claim that this contradiction matters to us when it comes to meaning of information. So a little bit, so this is the second assign within the assign, so a little bit of proselytizing about the role of theory. Ideally, I like to view the sort of theory as the foundations of practice. So it's not necessarily what you immediately, the algorithms that you design in theory, the compression schemes that you might find, or the encoding schemes that you find, you might not immediately rush to put that into practice, but it informs practice. Practice builds on it. So practice and the application layer sit on top of the theory layer, and the theory layer is the foundation. Unfortunately, for our communicating and computing devices, there are two different foundations, and they're both sitting at different levels. I mean, they're just completely pitched at different things. And what that leads us to is various options that we have to choose from. Would you like to build your house to look like that? Or maybe just abandon that other foundation and build it here, or abandon this one and build it there. Okay, so this is roughly the situation we are in. When you look at your phones, typically not programmable devices. You look at your laptops, they're typically highly programmable devices. And, one of them is sitting here and the other sitting there. So the good news is, actually, fortunately, we're practicing one of these two latter options and not this option one. But the bad news is that there are lots and lots of lost opportunities. There's vulnerabilities, there's inefficiencies, there's incompatibilities. There's just a whole mess of problems. And right now, the world is progressing as if these theory problems are theory problems and they'll go away. I'll just ignore it. Systems are working today, that's great. There is no guarantee that this will work tomorrow and we're fine. One of the nice things about theory is we can often make a statement about the products that we build today and how they would work tomorrow. And we don't have that. So let me tell you about a couple of cases where I would like to have a little bit more robustness in our devices. So universal printing. I would like to take my laptop, come to Stanford today. I have the permissions from the organizers, and now I should be able to say, look, I have this boarding pass, I'd like to print it. Unfortunately, this is not how it works. I mean, I have to take the boarding pass to somebody and get it printed. It's not the case that my machine can download the printer software and figure out which one it is and automatically just go ahead and print it. Why not? I mean, this is a sophisticated machine. It's an intelligent machine. Why can't it just go out there, find out the right software to load, find out how to get all the, use all the permissions that I have, and find out which ones will allow me to print. Doesn't happen today, and that's because our communication protocols are often dumbed down. We don't want them to think too hard about what they're doing. And the number of problems that you have projecting from laptops. I mean, this is a couple of devices talking to each other. That projector over there and this laptop of mine. How complicated can it be to wire these two so that they can understand each other? But we see the problems occurring often enough.
You might argue that that's deliberate, right? Because people want to create niches. They want to control all aspects of the ecosystems and so they want to create boundaries.
You could say that it's there's commercial interest, but on the other hand, the universality, I mean, I don't think at the end, the projector companies are coming up with some sort of a universal protocol. If they don't have it, then they're the ones who are going to get left out. So there's always this tension between the open source and the closed thing. And by and large, we've seen the more open you are, the more likely you are to win in this market. Interoperability seems to be a necessary condition for survival over here. And so people are not doing these changes for reasons of keeping it proprietary. I think these are basically very rigid protocols. They say if you specify things exactly in the following way, things will work perfectly. Any other error will be errors. and both my machine and the projector have specified the protocols exactly. Today they happen to be compatible, so it's working, but quite often we don't have the bits right, and then things, you see the issues on the thing. And the question is, why can't my machine search for the protocol that would work? And this is an ongoing quest. The final one is the one that I am most concerned about. We've rushed to convert all our forms of data, of textbooks and so on in the libraries into digital formats. On the other hand, the success of our dealing with digital data is the following. We know how to preserve the data for about 15 years. After 15 years, we would have lost the format. We wouldn't know how to read the thing. I mean, I have all my sort of daughter's photographs from her from 10 years old, which are on devices, and I don't have readers for those devices. They're on zip drives and so on. And it's just, there's just an amazing worry about how nicely are we preserving this data. And if you want this digital, all the papers that you write and publish today to be available 1,000 years from now, what are our hopes that this thing is going to work? Where is the theory saying that the format in which you have it today will suffice for you to read it 1,000 years from now? So we are really in dangerous grounds, and this is one of those cases where we'd like to build a technology today and know what it will take to make it survive 1,000 years from now. Maybe it won't survive without help from us, but we should at least know what it takes to make it survive. So these are issues that I consider in the sort of semantic space of information. And I want to start drilling down on what is the underlying question. So recall, in Shannon's case, he said the significant aspect is that the actual message is selected from a set of possible messages. And I want to say that right there lies the new kind of uncertainty. The sender and receiver are in disagreement nowadays about even the set of possible messages, for instance. Okay? And the moment you allow for even this one tiny possibility, you realize that many of the paradigms that you're working with suddenly don't apply anymore, and you have to reinvestigate. So I'll try to tell you about one concrete such problem shortly. But in general, modeling uncertainty, how should we do this? In the classical Shannon model, if there were two, sort of the sender and the receiver, A and B, are talking across this channel, then in the modern model, what we really want to do is replace these by a cloud of possible senders and receivers. There's A1 to AK, each one of which maybe acts and behaves differently. And there's B1 to B sub J, each one of which acts and behaves differently. And when some adversary possibly comes along and says, hey, AK, you should talk to B2, you should talk to some Bob over there. She doesn't tell you which one of these particular members that you're going to be talking to. So you don't quite know what a 0 coming out of this side means. If B2 was sending you a 0, it means one thing. If B3 is sending you 0, it means something else. And this uncertainty is what we're trying to deal with over here. So there are many possible ways of associating meaning to bits. Each one of these Bobs has a different association between bits and meaning. And what we would like to say is somehow use this channel to figure out who you're talking to and then make progress on the task at hand. So there's a new class of problems, there are new challenges, and they need more attention. So the first thing that I will talk about is a very basic problem in this setting, which is sort of modeling uncertainty between the sender and the receiver, and look at the new ingredients that it introduces. Okay. So this is a non-interactive communication task, compression. Alice has some message that she wants to send to Bob, and she doesn't quite know Bob perfectly well. So where in communication did we make an assumption that the sender knows the receiver? In compression, this comes out in the form of saying, I will assume a distribution on how the messages are sampled, and according to this distribution, I will compress the information. So this is how you get Huffman coding or something along these lines. And if we do it right, then if we have the distribution right, then we will be able to communicate roughly the entropy of the distribution, of the source distribution, many bits, and that will allow Bob to recover this information. So where is the uncertainty? Alice does not know what distribution Bob thinks the messages are coming from. Bob does not know what distribution Alice thinks the messages are coming from. This is where there's uncertainty, and let's see what kinds of question.
So Madhu, so how it different from universal compression when you have, several languages?
I'll get to it in a few minutes.
Great.
Just let me.
Okay.
And I want to suggest that this is actually a very common phenomenon in human communication. When we are talking to each other, and even in non-interactive settings, what's a non-interactive setting? You're writing a paper. Depending on which community you're writing this paper to, are you writing to a collection of high school students? Are you writing to Sergio? Are you writing to your advisor? Are you writing to a conference in a computer science and information theory? Depending on what assumption you make about the reader, you write a very different piece of text. Depending on, and this is the sort of aspect that I want to talk about. There was sort of more stuff on the previous slide, but I won't talk about it much. But I want to say that there's sort of behavioral aspects of natural communication that emerge over here. There's a vast implied context. I assume you know lots of things. Even as I'm talking to you, I'm assuming you know English. I'm assuming you know certain specific words in English better than the average person. I assume you have some sort of you know what Huffman coding means. I don't have to explain that to you. And I assume you know what entropy means. So this would not have flown in a different audience. In a different audience, I would have said a different collection of things. So there's context that's being used. And the sender sends increasingly long messages to the receiver till the receiver gets it. This is roughly the principle. Or till the sender feels that the receiver should have gotten it. The sender may use feedback from the receiver, but I won't assume that in this part of the talk. And the language is very interesting. Language provides us with many alternatives. If you think of the language as the encoder, as the code book, it provides us with many options for how to say one thing. Where is this phenomenon arising from? How can we pin it down? So why are we choosing sometimes short messages, sometimes long messages? The reason for short messages is the classical thing, compression. I don't want to spend 3 hours describing ideas which you would understand in half. And so the channel is still a scarce resource. We do want to use it optimally. But there is a reason to choose long messages, because I want to reduce the ambiguity. I'm not sure of your prior distribution, what distribution you're using. The less sure I am about your state of knowledge, the longer my messages will have to get. Can we mimic this in some mathematical example? And I'll try to do that in the next few slides. So here is what we want to design in this talk. We want to design an encoding and decoding scheme which work when the prior that we have on messages is not in perfect agreement. Okay? So this is the goal, and I'll try to elaborate on this in a few on this slide. So the sender has a distribution P on a message space, which is a set of integers. The message is one of n possible things. So this M, capital M, is a set of possible messages. The receiver has some distribution Q on the same set. So P and Q are not identical. Okay? So this corresponds to my background is in something. Maybe I'm even estimating what you know, but my estimate is some P. But what you know is some Q. Okay? Or a typical member of the audience knows is some Q. And I would like to make sure that I can send this information to you in some reliable way. So a natural way of sending this piece of information, some information from the set 1 to n, would be I can encode it as a log n bit string. That unfortunately wouldn't work for us. We would consider it much too long. It's not taking any prior information context into account. Maybe the entropy of P is very small. Maybe the entropy of Q is very small. Maybe these are actually the same distributions. We would like the messages to be much shorter if we can make such strong assumptions.
So what is assumed about what people know about P and Q? Do I know that you have Q?
Let me formalize this completely precisely. And so the sender gets a message, and the sender gets to send an encoding of X, but X is being encoded under the knowledge that I expect the distribution is P. Okay. With some slack. So there should have been a subscript over here describing the slack parameter, but unfortunately I didn't use it yet. We'll come to that in a few minutes. The decoder, on the other hand, receives whatever the sender sends. So just the encoding of X under the P distribution. It's a string Y. but it doesn't know Q. It doesn't know P. But it's allowed to use its own prior information, Q, into account, and it should decode to some message X hat in the same set. What it would like is what we always want, X should equal X hat, with high probability, provided P and Q are close. And this concept I'll try to tell you which definition of closeness we will use, but this is roughly the goal. And what we would like to do is minimize the expected length of the encoding. Okay. Expected under what distribution? Let's assume the sender had it right. So let's say under the distribution P. It doesn't matter much if you want to minimize it under Q or some arbitrary distribution R. We want to minimize this. Okay. So this is the concrete problem. Does this make sense? If you have any questions, this is a great time to ask. It's a very simple question, and this tends to model roughly what we do in natural communication.
Is your view of P as a finite object, or is it like, even distributions on a set of 2 points is a continuum?
Sorry?
So is P is basically some real valued object?
Right. So P is a n-dimensional vector in, right?
So do you assume some regularity properties?
I'm not going to assume anything. In fact, so this is where it differs from, say, something like universal compression and so on. I'm not assuming that I have long sequences of messages from this space. I have one message and I want to send it to you. So I have one option, this 1 hour to give this talk, and that's it, no more. I don't have this P is sort of all the knowledge and wisdom I've collected over the last 45 years. It's not something that I think can be represented in any succinct way. It's not generated by a finite state Markov process. It's some arbitrary distribution on n letter, on a universal size n.
So the question was whether E is assumed to be continuous, for instance.
E, yes, we'll have to make some reasonable, when we come down to, what's the space of functions over here, it'll be nice to say it's not necessarily, P can be sort of approximated by some discrete space, etc. But we won't worry about it. It won't sort of pop up. It's there implicitly that somehow a close enough approximation to P may be made by all of us. We might all agree. So this model certainly allows us to discretize P and Q simultaneously. We might both agree and say, look, anything that comes along will finally sort of truncate the real numbers in P to some finite number of bits. We can do that. It's completely legal because I just defined E and D to do this simultaneously. E and D are designed jointly. Okay? So it's completely fine. However, once the encoder and decoder have been designed, then you find out what distribution you're going to have to work with. The receiver finds out what distribution it has to work with, and the two of them are not the same. And we cannot make the assumption that they are the same. So all we want to say is, well, as long as P and Q are close in some metric, this encoding and decoding should work. All right. So contrast with universal compression, we are not assuming P and Q are somehow succinctly specified. They are specified by an n-dimensional vector and no further assumptions. And n bits of communication is too much. Log n is too much. We really want to do something which is the entropy of P or related such quantities. And we think of entropy of P as sort of vastly smaller. So of all possible if I want to send you a paragraph long email, of all possible sentences of, word sequences of the length of the paragraph, only English ones relevant to our, interests are going to be in the support of P. Okay, so it's very, very, the entropy of P and Q should be viewed as much, much smaller than all of the universe size. And KL divergence, people often say, well, there's P and there's Q, and should we just measure the divergence between the two? Maybe, but divergence does not tell us, it tells us how far these distributions are, but it gives us no idea how to use this in the current setting. Usually you apply divergence when the sender and the receiver both agree that the distribution is P, and it turns out to be Q. Then it tells you how inefficient you are. But they are in agreement. There is no disagreement between the sender and the receiver there. Here we don't agree on the distribution. Okay? So this is why these things are different. And so what's the measure of closeness? I'm going to use the following measure. I'm going to say that two distributions are alpha close if point-wise for every possible message I have the ratio of the two probabilities, the p assigns to x and q assigns to x, are within a factor of alpha. Okay? So let's start by thinking alpha equal to 1. P equals q. Okay? If alpha is 1, then we are in perfect agreement. If alpha is 1.01, then our distributions are almost the same. But we have slight disagreement about what these probabilities may be. For the purpose of the talk, think of alpha as 10 to the 5. Okay? Big number. These are all differing by vast amounts, but it's still, you know, it's a manageably small quantity. There's a question.
I mentioned very briefly this. Usually we have the same requirement for differential privacy.
Okay, we have an expert in differential privacy. Is that right?
Yeah.
So this is okay. So I wasn't aware.
Can you repeat the question?
The question was this is the same, or the comment was that this is the same requirement that's used in differential privacy. It's a sort of there's a notion of dominance of distributions that's used in computer science quite often. It goes back to Levin from the mid-80s, and there you would focus on, say, the left-hand side of the inequality and say that's an important quantity to worry about. Here we're symmetrizing this thing because it makes life easier for us. I didn't realize it was close, but you know, it sounds good. For those who work in information theory, this is probably an unfamiliar requirement. So let me tell you what it implies. It implies, if P and Q are alpha closed, it implies that the divergence between the distributions, either way, I mean, the divergence of Q relative to P or P relative to Q are both at most log of alpha. Okay, so they're both under control. And this is in some senses an L infinity norm on some quantity, and divergence tends to be the sort of L1 norm on the same quantity. So it's really, you know, you're looking at a vector, one of them looks at the worst possible value that it can get, and the other looks at the average value that it can get. So it's related, but it makes more sense from our point of view, because we have noticed that we never make any assumptions about where the x actually comes from. We just tell you that if it came from the distribution P, then the expected length of the compression should be small. If it came from some other distribution, you should still be able to send it. You might be sending very long strings. That's how things work. I mean, okay. All right, so this is a measure of distance that we want to have, and we want to say that, look, the sender and the receiver will agree on alpha. Okay? So we agree how much we disagree, and then we try to say how to compress the information. Okay? And what I would like roughly is that if alpha was small, 1, then you would get perfect compression. If alpha is very large, then we agree that we sort of are disagreeing. We get compression which is not as short, but somehow scales nicely with alpha. As alpha becomes larger and larger and larger, there's more and more and more disagreement between us. The message length gets larger and larger, and this is what I'd like. And this is what we will deliver. 3 easy steps. Now, one thing that enables a lot of human communication is some notion of a common dictionary. We have the dictionary of English. If I want, I can activate the dictionary of science, and so on and so forth. And the dictionary gives us some very useful constructs, which we will model very crudely and very simplistically today. This is not a great assumption, but it's a good assumption to help us make mathematical progress. Okay? And the way I'm going to model the dictionary is that it somehow is giving us one large common random string that we can both work off of. We are in perfect agreement with the source of this particular random string, and the string is truly random, a sequence of random bits. And so I'm going to allow it for today. I don't think it should be required in an ultimate solution, but that's actually an interesting mathematical question as to whether it can be done. So we're going to have this common randomness, which means the encoding is allowed to say be a function of the distribution that you think the message is coming from, the message, and this common randomness. The decoding is also allowed to be a function of the distribution that you come from, the received sequence y, and the common randomness. So the randomness is chosen once and for all without knowledge of P and Q. Then P and Q come after, and you have to do something. Okay, so this is how things work, and we would still want with high probability over the randomness that x hat is really x. Okay, does that make sense? So adding a little bit of mathematical. And now this is how we come up with the solution. This is some variation of arithmetic coding, I think, but maybe also actually related to the Shannon coding scheme that we saw in the morning, but I don't quite have my references right, so I don't know. Here's what we're going to use this common randomness to do. The common randomness, we will use it as saying, I'll tell you how to write the message 1. You know, remember our message set was 1 through n, capital N. For each one of those, I will give you an infinitely long sequence of bits, which tells me how to describe it. Okay? And so R1 of 1, R1 of 2, R1 of 3, etc. goes on forever. Infinitely long just because we will be able to truncate it soon, but that will just mess up our thinking if you put the bounds now. So just think of it as goes on forever. And similarly, an infinitely long sequence of bits. So think of R as being this bit followed by that bit, followed by that bit, followed by that bit. And then this, etc., etc. So I just wrote it in a different matrix form. And now I get a sequence as long as I want of bits which describe the first message. I get a similar sequence of bits which represent the second message and so on to the nth message. And both you and I have agreed these infinite sequences represent these messages. So how am I going to send this thing? I can't afford to send infinitely many bits when I'm complaining about n and log n. Infinitely many bits seems to be too much. So what am I going to do? I'm going to send the prefix of this sequence and stop at some point where I'm confident that you should have gotten the message by now. How do I define how long the sequence should be? So I will encoding under alpha of some message x. Little x represents a worst case message, capital X requires a random variable. So for a little x, how do I encode it? I will send the first capital L bits, L depends on x, where L is chosen so that when you look at all the sequences over here, which have the same first L bit sequence over here. Okay. So maybe L turns out to be 3. So I look at all the messages which go, and maybe I want to send the message 1 to you. So I say, well, this is 0, 1, 0. Maybe that's what these 3 bits were. So I look at all other prefixes which say 0, 1, 0. Well, probably 1/8 of these sequences will say 0, 1, 0. But why do I stop at 3 bits? Because I see that every other message which has the same 3-bit prefix has much lower probability under my distribution P than the first message. Okay, so that's when I stop. So the encoding is a function only of P, X, and R, and it says send the first L-bit sequence, where if you look at every other Z, which happens to have, so every other Z, either the first L bits are different, in which case no chance that you will be confused with Z, or it turns out the probability that I associate with Z is significantly less than the probability that I associate with X. How much less? By a factor of alpha squared. Does this make sense? Yes?
I'm having a bit of trouble understanding a concrete manifestation of what R would be. For instance, let's say that you're writing papers today and you want somebody to be able to read it 1,000 years from now. Like, what is R?
Okay, so then we have to make an assumption on what kind of dictionary could get passed on. So firstly, I think of it as a communication between me and you today. And so maybe I can refer to the common dictionary that's available, it's the Webster's, etc., and so on. But the dictionary doesn't, has many words, and think of the dictionary as informing how I would write a paragraph. So the dictionary does not cover all possible paragraphs that I have.
So you meet me somewhere, and then there happens to be a dictionary lying around. You say, hey,
or you've seen the dictionary in the past. I have seen the dictionary in the past. We have a common understanding of these things, and it is implied that when I say field to you, it's a mathematical object, not a farm. And so all these things are sort of grounded into this thing. So there is a, the translation from the message in my head, which is some abstract object, to a sequence of bits, somewhere it has to be done, and the dictionary is doing it for us. Okay. And the dictionary is somehow common, but then the distributions come and taint us. So maybe if I don't know quite what your background is, and I don't know you're a mathematician, I might not jump to the assumption that you would realize that the group is also a mathematical object. So the distribution comes along and says, can I use group? The group is sort of G-R-O-U-P, is the prefix associated with this abstract object in my head. But then I might follow it up with the thing saying, oh, the mathematical structure, if I don't know that you're a mathematician, or how much of a mathematician you are, etc. So the dictionary is our common understanding of words and how they should be explained, and it's a longer and longer and longer description depending on how much commonality we have. Okay, so natural language, we tend to have this association saying, there is, for any concept that I want to describe to you, there is a longer and longer and longer string which is infinitely long, which will completely clarify that word to you. However, it's not a sequence of random bits. Random bits is convenient. All right. So this is the encoding scheme. And what is the decoding scheme? It's obvious maximum likelihood. But it's maximum likelihood under the distribution you know, not the distribution that I encoded it under. So you just look at all the strings x hat, all the strings z, whose first L length prefix is y, and you look at the set. This is a set of all candidate dice. Which one of these dice should I pick? The one which has the largest probability. Okay, completely natural thing to do, and it's a sort of a simple exercise to see that this actually works correctly, under the assumption that P of x and Q of x are related by a factor of alpha. This will always reproduce the message correctly. And it's also a fairly simple exercise to show that the expected length of the compression is the entropy of the distribution P plus twice log alpha. Okay. Yes?
So when you say that the distribution are related by a factor of alpha, you mean the divergence between the two distributions is within a factor of?
It's a little bit stronger than the divergence between the two distributions. Okay. It's a symmetrized divergence, okay, and it's a sort of a worst case divergence. So for every possible, so it's something that implies that the divergence is bounded by alpha, but it's a more technical condition. So this is the one that I was talking about here, right? This condition. Okay, so for every point, these two ratios are bounded by alpha and 1 over alpha. But alpha can be pretty large, 10 to the 5. What does 10 to the 5 mean? It means that I would have to add twice log of 10 to the 5, whatever that is, about 30 bits to the length of the string in order to convey this information to you.
Also, just technically, how do you analyze this and then decode it? Do you just,
oh, it's very simple. I mean, it's sort of baby discrete algebra.
Okay.
It's really very simple. Okay. So I didn't do it, but it's an easy exercise to say that this is the expected length of the encoding. And notice that this has got all the right features. When alpha is 1, the two of us are in perfect agreement, or we think we're in perfect agreement. Then you get the entropy of, okay, there should be a plus order of 1 here, maybe plus 5, I forgot to add that. But it's entropy of P plus some constant. Okay? And this is one-time usage of a message. We are not doing this over a sequence of messages and amortizing and so on. This is just once. And on the other hand, if our distributions are somewhat divergent, there is an option of using a longer sequence to convey the effects. So this is roughly what happens in this setting. We can prove that there is no scheme, no D and Q, which for all, no encoder E and a decoder D, which for all possible pairs of distributions P and Q, where P and Q are related by a factor by distance of alpha, will achieve a compression length which is 1 minus epsilon times entropy of P plus log alpha. Okay. So we can prove some statement of this form. So this is roughly the right behavior, except for this factor of 2, which we can't really explain. And the randomness that we have, I mean, infinite is not necessary. It can be made much more finite, and roughly log n, order of log n bits of randomness really suffice, but that's not too crucial. One of the things that we are working on is trying to make the scheme really deterministic, and that's a kind of an intriguing mathematical question, but I won't get into it today. So I'll probably, how much time do I have? 10?
Probably more. I'm not
Okay,
sure.
let's do 10 minutes, and people will eventually want the day to end also.
4:30, yeah, you have 10, 15 minutes.
10 minutes. It's, all right. So one of the nice things over here is, you know, by modeling this uncertainty, the sender and the receiver did not understand each other perfectly. We came up with a scheme which has a lot of effects similar to that happens in natural communication. We are using some redundancy, but the redundancy is not the kind that you used in error correcting codes. It's very different. I sort of say a little bit more depending on how much commonality in background I'm assuming. So there's some very interesting features which I think is nice. And the shared randomness, I mean, it's an assumption that it's convenient to make progress, but I think eventually we should get rid of it and try to see what else could have worked. So this is roughly what I wanted to say about this one concrete problem. It exemplifies the kind of problems that occur when senders and receivers are uncertain about each other. The broader question I want to ask is really, suppose I wanted to write a text today and assume, digitize it and hope that many, many years from now people who are reading it can figure it out. What should that theory look like? What kinds of assumptions should we be making? What kind of assumptions are reasonable and realistic? And that leads to one of these questions that I'd like to ask even in the interactive setting. I don't know. So imagine somebody from an alien universe comes and starts beaming bits to us. How do we try to understand what they are saying? And when we haven't had the time to establish a prior context, if we can really get over having the common dictionary, the common sets of assumptions and modern uncertainty in its fullest extent. And so when the sender is sending instructions, can we make sure that the receiver is figuring out the right instructions to follow? And like I said earlier, this kind of a idea of, how do I associate meaning to bits? We do know how to do it, and there are plenty of ways of doing it, and the Turing theory tells us exactly how to do it. The notion that there's a universal computer, what does it say? It says I can describe any other functionality, any other algorithm to you by a sequence of bits, and then the universal computer can interpret the sequence of bits as a collection of algorithms. So there is an association of bits to meaning which makes sense, which is very mathematical. Let's see what happens in that context. The issue is, Turing also proved, and everybody else since then has noticed, that there are infinitely many universal machines. And depending on who you are, you have a preferred universal language. You might prefer English, you might prefer C++, whatever language you want, that's a language that you want to work with. And we can never come to agreement about the one language which will work for all of us, right? So it's this proliferation of languages that's the problem. And the question is, can I somehow describe this to you? And people in the past, the ad hoc solutions, what do they tend to do? They say, well, okay, so if I want to store this document for many years and I want to tell you that, look, this is a PDF file, then I will also store the PDF program, the reader, Acrobat Reader or whatever. Okay? So I will store the code of that program also along with the document. And now you have enough information to read it. Unfortunately, no. You have to tell me which programming language you wrote that reader in. Okay, so I'll also put in the compiler for that language. Compiler compiling from what piece of hardware? So, and we keep going backwards and backwards and backwards, and there is no end to it. So the theory actually tells us that there is no finite way of describing this piece of information in a non-interactive way. So maybe interaction might help us, but that's the only thing that could work. And unfortunately, so it's easy to prove this negative result, saying that in finite time I can't give you instructions which can be unambiguously interpreted. This does not work. If I want to allow a diversity of thoughts amongst you, that you want to pick any universal language that you feel like, then unfortunately I'm in deep trouble. And on the other hand, one of the nice things that we try to elaborate in this theory, which I won't talk about, but just give you an advertisement and a pointer, is we started saying, look, I mean, but you know, the goal of communication was not to exchange a collection of bits, and I'm not, the reason you are programming your machine to do new things is because you are an independent entity. If you wanted to be controlled by me, I would be very interested in making sure that the instructions that I send are interpreted correctly and faithfully. But if you are doing things on your own, the reason you're probably communicating with me is to do things that you think are profitable. That there is some value in the communication to you. And this value in the communication is what we should try to attempt to define formally and measure precisely and see if you're making progress along these things. If the communication, if your goal is to take a course with me and you want to learn what I'm saying, then at the end of the course, you're able to solve problems that you couldn't solve earlier, then you profited. Maybe you did not understand everything I was saying, but if you're able to solve new problems, then you made progress for yourselves. And it's this kind of a theory that we try to formalize. We did this under the lens of computational complexity, and I'll try to tell you briefly the spirit of this work. This will be sort of informal and ad hoc. It's all formalized in the work. But roughly, how does computational complexity try to analyze questions of this form? When it says, you know, how can I try to say that communication was useful to me or to you? We say, well, okay, maybe the goal is the following. I'm a cheap laptop. I'm sitting out there communicating with other servers out there. And the reason is because I want to solve some hard problems that are very hard for me to solve on my little laptop, but maybe there's enough computational power out there to solve it for me. So the way we try to look at these kinds of questions is we say, what are the hardest problems that we can solve without a particular resource? If you want to prove some resource is useful, so traditionally in computational complexity, you applied it to the memory space that's available to you, or the amount of time, or the CPU speed. And today we will apply it to communication. So my machine is now communicating, and it communicates either with understanding of what you're saying or without understanding. Is this beneficial? In what sense is it going to be beneficial? With the resource, I can solve more problems or harder problems than I could solve without. Then communication is useful. So we try to use this kind of a model of the lens of computational complexity to understand whether communication is an interesting and useful resource. And roughly what we can say is that, okay, I won't try to dwell on that. What we were able to say is that, look, if I'm communicating with some very, very powerful other server, and I know exactly what the server, how to describe problems to the server and how to interpret the answers given back by the server, then there's almost no bound to the kinds of problems that I could solve. On my own, because I'm a small laptop, I am very much bounded. But if we try to sort of say, well, I don't really understand the server, and I'd like to figure out what the server is doing in the process, then there is an interim region of problems that I can solve. It's more powerful than what I can solve on my own, much less so than what I could assume by perfect understanding. And the sort of recurring phenomenon is we should trust, but we should check. We should keep checking our understanding of the server and do this. So all of this can be actually formalized nicely mathematically, but I won't do it today. And many of the lessons over here is that at the end, we can imagine settings where you can design a user and a server. A laptop which is talking to other devices, and a server which is trying to provide service for other devices independently, and let them somehow interact with each other and converge on somehow common protocols, as long as there is sort of feedback, enough feedback in the mechanism for us to realize, are my goals being satisfied? Are the goals of communication being satisfied? And throughout there is this thing saying, well, server and user should always sort of plan for uncertainty. There is a possibility at each stage that you may not be understanding what the other person is doing, so check your actions. And there's a sort of a recipe for how we may be able to check. Whoops, let me just jump to the conclusion. conclusions. So one of the future goals over here is that we can do sort of an information theoretic study of phenomena which arise in human communication. And a lot of phenomena that arise in human communication is surrounding this issue of uncertainty. I don't know quite what the other person is saying, the other person doesn't quite know what I'm saying. Equate that with saying, I don't know who you are and you don't know who I am. And these kinds of questions are mathematical in nature, or we can put some mathematical flavor to them. And they not only can be modeled, but actually they start to explain why human languages tend to look the way they are. I think this is an area of fruitful exploration. And on the other hand, if you sort of study human interactions and how they're working, there's also a sort of an alternate paradigm for these design communication methods, where we commonly design encoders and decoders. There may be alternate protocols out there, and which we should explore and exploit. So I will stop here. Thanks.
David, you have a question. David, you have a question.
Let me start with
I've already asked many questions.
Right. Let me start from the back and then on.
What were you assuming about the randomness R in these results?
Oh, in the compression scheme, what was I assuming about the randomness? It's perfectly independent collection of bits.
Okay.
So that was used in the analysis, saying the compression length is as small as it is, and so on. You could sort of relax it in various ways.
Could you give one-line idea about the converse, that you cannot do better than like 1 minus epsilon times HP plus log alpha?
Yeah, I mean, because we're working in a, so somehow you can sort of, you can model this as a combinatorial problem with, certain very simple class of distributions, P's and Q's. You sort of put them on a space, put them edges between them if they're within a distance of alpha, and somehow come up with some simple pigeonholing argument. I don't remember the exact details. It's not really sophisticated.
So, looking at this compression discussion, there was only part that I understood, because the last part was too fast.
Speak louder,
No, the compression discussion. So it seems to be more like a theory of statistical robustness than what you might call a theory of semantics. Because semantics, normally one has a notion of concept classes which are represented through some syntax, and you're trying to convey concept class, right?
I agree. I mean, there is a, what are the, I don't want to put a particular expression labeling semantics, so semantics is part of the issue, but I really want to say what are the issues that drive natural communication amongst intelligent devices. And some of the issues are issues like the uncertainty and the robustness. So yes, it's a robustness question, but isn't all of communication.
Are you also interested in the issue of trying to say merge what people call semantics in the CS literature with information theory? So that's an interesting direction.
So what people have referred to as semantics in the CS literature tends to not allow for this. So the choice issue, what is the language of choice for me, is not modeled in the CS semantics literature. That is the fundamental issue that I'm trying to get to. I want to figure out how to associate bits to meaning, yes. In that sense, we are similar in quest. But the problem that's coming up in communication is that we all choose different maps between bits and meanings, because that's somehow more, one of these we prefer more. And what are the reasons for our preferences? Why are we diverging? These are the issues that I want to get to. And the last part, which I was just sort of advertising that there is other stuff, is really dealing with these kinds of questions, but unfortunately it deals with it in a level of generality which is a little too much. Any other questions? All right, thank you very much.
Thank you.